that we're taking our knowledge of the easy cases, the concrete cases, where we first acquire a notion of large, and we're kind of repurposing that knowledge to usefully talk about things which are not immediately in front of us. And that ability, I think, underlines a lot of human cognition, and I wouldn't be surprised if it being a sort of key part of why we are clever. I think that finding structure in time is maybe one of the most important papers in the history of cognitive science. But because I've kept the language and vision data separate, I can then I can look up according to the language and return the relevant experience that I experienced visually at the same time. But that's very controversial, so I'm saying that as a sort of spicy take.
Hi everyone, this is Axel. This episode I have Felix Hill with me. Felix did a PhD in computational linguistics at Cambridge and currently works at DeepMind as a research scientist. After finding out about Felix's background, I bring up the concept of compositionality and we explore why natural language is non-compositional. Then Felix tells us a bit about his work in Cambridge on abstract versus concrete concepts and gives us a quick crash course on the role of recurrent neural networks, RNNs, long short-term memory, LSTMs, and transformers in language models. Then we discuss the core of Felix's work, which is training language agents in 3D simulations, where we raise some questions on language learning as an embodied agent in space and time, and how something similar to Allan Paivio's dual coding theory could be implemented in the memory of a language model. Next, we stick with the theme of memory retrieval and discuss Felix and Andrew Lampinen's work on mental time travel in language models. Finally, I ask Felix on some good strategies on how to get into DeepMind and the best way to learn NLP. As usual, if you want to skip ahead to any specific questions, there are timestamps in the description. Enjoy. Hi Felix, it's great to have you here. How did you get interested in language and natural language processing, NLP?
Yeah, thanks, Axel. It's really great to be here and really fun to come and chat with you about some questions which I find really interesting. In terms of how I first got interested in all this stuff, so I did an undergrad degree in maths, and potentially paradoxically, I really preferred pure maths. I didn't really get drawn too much to applications of maths. And I think that was mainly because, well, firstly, the introductory courses is to things like statistics, so I think quite boring. And the second reason is because I don't really have good intuitions about the physical world. So I'm probably a rubbish physicist. And that reflects itself in the fact that I think a lot of the assumptions that you have to make in doing things like a physical applied maths, I always found them a bit arbitrary. I couldn't understand why it was okay to assume one thing but not another. Whereas in pure maths, like, you kind of just wrote down the assumptions almost like as a game, the axioms, and then it was kind of all about your ability to reason from there. So I really liked that. But I didn't like it enough to want to do it for research, really. And frankly, I almost certainly wasn't good enough. So, in those sorts of fields to do new research, you can almost quantify how good you are relative to other people. And I was reasonable, but not good enough to be the smartest. And so I looked to do other things, and I actually went off and did non-academic stuff. So I worked in some corporate job for a while, and I was a maths teacher. But during that time, I felt somewhat unfulfilled. So the corporate job wasn't particularly interesting from an intellectual perspective. And I love teaching, but I almost envied my students who were kind of still in this journey of learning new stuff. And I kind of wasn't after a while, right? Because I was, especially as a maths teacher, you really are teaching the same thing every year. I didn't really feel like if I did it for the next 40 years, I wasn't sure whether I'd really be fulfilled in the sense that I wouldn't be learning much new stuff myself. So kind of selfishly, I looked for ways to maybe do something for a few years and then, of course, potentially go back to teaching. And I might still do that. So I wanted to go back and do something intellectually challenging, but I didn't love pure maths enough. And I started to get very interested in language. And I think the reason is because I do like people. So even though I don't understand the physical world, I quite like thinking about the social world. And so I was kind of interested in language and people, but also in maths. The natural choice was to start exploring academic disciplines in that space. And I did a bunch of reading. I watched Steven Pinker's very well-known TED Talks, and I read a lot about Chomsky, because if you kind of think about the interface, at least back then, the interface between mathematics and language kind of takes you towards Chomsky. But strangely, after a while, I kind of came to the realization that although Chomsky is in some sense combining maths and language in his research, it also seemed to be pretty much all wrong. And what started to fascinate me was the ways in which natural language was totally different from mathematics, or different in really interesting ways. And I felt like Chomsky was trying to force a similarity there between language, natural language, and formal systems that didn't really exist. And actually, I mean, I'm definitely not the first person to think like this. And in fact, it was very influential. Other people, cognitive linguists like Lakoff and Langaker, and also even Wittgenstein, right? So I guess Wittgenstein first initially was kind of set out to do something similar in the sense that he was from Russell's tradition of formalizing philosophy of mind, but he realized that it seemed somewhat futile and that there might be a different, more productive way to think about language. So I was getting really interested, and I looked for programs in graduate school, and I managed to get into one in Cambridge. But this is relevant maybe to other people who are at this sort of stage. I'd never written a line of computer code in my life, right? And I was like 26 or 27 at this time. But on the other hand, my brother was a software engineer who'd done a master's degree, and he told me, for someone with your background, basic programming should be pretty easy. Now, that's not to say that expert programming or good quality software engineering is easy, but just that the sort of programming I might be interested in doing wouldn't be too hard. But it was hard to apply to graduate school without any credentials in this area. So I ended up doing a master's in linguistics in Cambridge. But the linguistics was very applied in the sense that there was psychologists, cognitive scientists, and computational linguists all chipping into this course. So it was kind of designed for people who were interested in more than just linguistic theory. But it certainly wasn't going to be a strong grounding in computer science or machine learning. So I had to do that myself. So during that year, I obviously took all the courses from the master's program, but I also spent a bunch of time contacting people in the computer lab and trying to get myself somewhat established there, and kind of often lying about what I knew about computers, because I knew almost nothing, but I did know some maths, and I kind of just tried not to betray how little I knew about how computers work. At the same time, I was kind of like frantically reading the Python textbook and the NLTK textbook from Edinburgh, and like trying to learn how to write code. And I think it's quite amusing, some of the things I used to do, like sort of writing loops over infinite sets and things like that, which all came from a maths background, right? So I was just trying to do some universal quantification or something, but obviously that doesn't work when you have to implement these things in physical reality. So I've made a bunch of mistakes, but I guess the lesson, if there is one, is that it can be useful to like not respect the curriculum of the course you're doing and instead do your own thing. And I think that's very true in British and potentially all European universities. You get a lot of freedom and you should use that freedom. So I did that, and then I was in the computer PhD program in computer science. So I got into the PhD program in the computer lab and kind of took it from there. So yeah.
Awesome. So yeah, Wittgenstein is actually what got me interested in NLP, reading him. But it's interesting that you said that at first you weren't really interested in the sort of the physical aspects of language, because actually what we'll talk about a lot later is language grounding in 3D simulation, which is all about, well, being physically in space. So I think that's quite interesting. Before we talk about NLP, I have a question about linguistics. So in linguistics, there's this idea of compositionality, which you talk about in your blog called NonCompositional. And what is compositionality, and why is natural language not fully compositional?
Yeah, so this is a very hot topic at the moment, and something that lots of people are discussing on Twitter and other things. So I would say, if we were going to try and define it loosely, it could be something like the idea that the meaning of a complex expression in language, natural language, can be derived from the meaning of the subparts of that expression. So that might typically be the words, and a rule or some rules which tell us how to combine those meanings. If there is such thing as an agreed upon definition, I would say it might be something like that. And to give an example of this working, we might think of like a logical expression, right? So if there's an expression of first order logic, like A and not B or something like that, then in order to evaluate that expression, we just need to kind of know what A is, and we kind of need to know what B is, and then we need to just know how the and operator works and the not operator, and then we can easily compute the unambiguous meaning of the final thing. So that would be an example of a system of a language which is working in a really compositional way. The rules here would be like, the rule would be the rule of how and works and the rule of how not works. And then knowing what A means and B means is sufficient to know the meaning of the whole expression. But it turns out when you think about natural language, and this is the point I'm trying to make in the blog, this is almost never in general true. So the way to work out the meaning of a natural language expression is almost never a matter of working out the meaning of the inputs and applying some rules. If you go to the blog, there's numerous examples of where this breaks down. But you know, just as simple as things like, if we talk about a big number, that's very different from talking about a big car. So what's the rule there that's telling us how to combine big with the meaning of the other thing? And then people like to talk about longer phrases, examples such as man bites dog. This is often used to show an example of the regularity of language, because we know in this case, the man is the person doing the biting, and then the person is biting, and then the dog is the person being bitten. But there's also a load of different things going on in constructing a scene which tells us exactly what's happening there, right? So the act of biting that a man does to a dog may be very different to the act of biting that a dog does to a man. Often interpreting all of these things requires us to understand how word order interacts with the meaning of the language, but it also requires us to understand how the world works and what is a likely way that a man would attempt to bite a dog and all of those things, right? So there seems to be lots of information coming into our understanding of constructing this meaning, which isn't present simply in the words themselves that go into the expression, and also potentially isn't present in some finite set of easily to explain rules. So in that sense, I would say that language isn't compositional. And if you go to the blog, you'll see many more discussions and examples of topics around this issue. Having said that, there is some regularity in language, right? And so the idea that language is not in general compositional doesn't mean that there is an interesting regularity, interesting effects of the order of words on what something actually means. So for example, we know that man bites dog definitely means something different to dogs bites man. And these regularities do seem to play some role in what's called productivity. So productivity is the idea that we can make sense of language expressions that we've never seen before by combining the meanings to create some meaning, of a sentence that potentially involves arrangements of familiar things in totally different ways, right? Totally unfamiliar ways. The idea that saying that language is not compositional, I think, is very different from saying that it's not productive. I don't know if you've been on the internet recently, you'll have seen lots of interesting outputs from these new image and language models like DALL-E or Imagen. And what people find most compelling here is to give these models sentences which almost certainly are not in the training data, right? So they'll say things like a llama underneath the water in a swimming pool smiling with a palm tree in the background or something like that. And it's almost certainly the case that no such image exists in the world. But yet these models can render a pretty plausible image of that scene. And that's an example of these models being productive. And we can definitely do that as humans. And indeed, that's one of the beautiful things about language. But it's absolutely not the case that because we can do that, it's necessarily a fact that we construct the meaning of expressions by putting in the inputs and applying some simple rules, right? In fact, there's a very interesting linguistic theory involving something known as frames or potentially constructions. This theory is inspired by examples like, I sneezed the pen off the table. Examples like this are intended to show us that in actual fact, what we're doing when we're coming up with an understanding of a phrase like that, which we may well never have heard before, is we're understanding a general construction, something like I sneezed the X off the Y, I verbed the X off the Y. So rather than sort of understanding some rules, we're understanding a much more abstract thing, which is a sort of abstract high-level pattern, which we develop experience of through our experience with the language. And then when we come to put in new words into that pattern and make sense of an unfamiliar whole, it's really not a question of applying rules, but rather of a sort of very complex constraint satisfaction problem where we merge in our understanding of pen, our understanding of tables, our understanding of what it means to sneeze. We merge that into our understanding of this pattern or this frame or this construction, which is a very abstract thing. And then they kind of compete with each other. So there's like a competition to fit it all in to what, according to our model of the world, is the most plausible interpretation. So that's a very complex process that's absolutely nothing like applying rules to the inputs to get an output. And that's just one linguistic theory. But I do think that one of the reasons neural networks and deep learning has been so effective at modeling language in the last sort of 5 to 10 years is because they allow for a process which looks a little bit more like that theory and a little bit less like what people typically think of when they think of compositionality. And I'd also like to ask, so there's a lot of debate and criticism of recent models, these models like DALL-E and Imagen. And the criticism is that they don't perform in compositional ways. They don't seem to behave in this way where if I swap something out and apply a new thing to the input and apply some simple rules, I'm going to get a very expected output. And that's certainly true. But I do think it's worth asking why we even need a model to do that. I've already explained why we don't need that sort of regularity in order to achieve productivity, in order for the models to be able to generalize to new things. So if we don't need it for that, then what do we need it for? And I kind of think that really we just need it so that our models can achieve a sort of idealized intelligent behavior, which socially and culturally we've come to hold on a pedestal. And that's precisely the sort of thing that children who have particularly a Western education are taught in schools, right? We're taught to follow rules. We're taught to be regular in our thinking. We're taught to extend patterns, which we've agreed as a culture are important in predictable ways. And as a consequence of our education, we start to do that. But I just think it's worth reflecting on whether or not that's actually a sign of being more intelligent and whether or not that's essentially something we want our models to do. We may well want that, but I don't think it's a sort of analytic truth that we want that.
Yeah, why do we want that regularity? I'm from a sociology background, and I think one could probably get into like endless debates and trying to situate this in sort of rationality discourse in the Renaissance era and all of that, and then how that frames our expectations about what intelligence, about what AI should be. But I have lots of questions, so I'm not going to get into that. But it's worth mentioning with the DALL-E and the Imogen, and also from DeepMind, the recent thing about Flamingo with images and language models coming together. Besides it being really interesting, it's also really cute because one sees loads of images of teddy bears and animals in different really weird contexts, and then the models tries to interpret that. So Twitter has been really fun recently. But it's worth saying that this afternoon I'm recording an episode of Alex Laskaridis from Edinburgh, and we'll talk more about compositionality and sort of formal aspects of linguistics. So if you're listeners, if you're interested in that, we'll talk about that next time. But now I want to get into NLP. So you mentioned earlier that you did a PhD in Cambridge with Anna Kohonen, and some of the work you did there was about comparing how abstract and concrete concepts might be represented differently in the brain. And could you tell us a bit more about this and how this relates to the semantic relatedness versus semantic similarity distinction in NLP?
Yeah. Okay. So it's been a while since I've thought directly about that. But yeah, just to be clear, so it's worth defining what I meant when I talked about abstract and concrete in those days. So back then it was literally, I was working on text-based NLP. So I was interested in thinking about which of the words in language refer to something directly physical that we can perceive through our senses in the world. So an example of a word I would have considered concrete is like cup or table or pen or something like that. But of course, there are many words in language which you can't really see or feel or touch. So an example of such a word would be the or by or in. But there are also nouns which are definitely abstract. So, things like democracy or war or discussion. And it turns out that if you read adult language and try to sort of just count what proportion of the words seem to be concrete versus what proportion of the words seem to be abstract, it's actually a tiny proportion of the words that seem to be concrete. We spend very little time using language to discuss the physical world as adults. When you look at child language, the proportions are quite different. Children focus very much early when they're first learning language on the physical world. So this suggests that there's kind of these stages of learning where as we're developing our conceptual understanding of the world as children, and indeed as we're developing our ability to use language, we're first understanding the physical world. And we're also understanding that other people see the physical world and understand the physical world. And then we're building on those concepts that we've acquired to slowly develop an understanding of the more social or the more abstract world. And if this is correct, and it's a huge simplification of what's actually going on, I should say, but if this is kind of approximately correct, then I think there are interesting implications for the idea of how we could build a language understanding machine. We might need, for example, a machine that has some exposure to the physical world, some exposure to grounded things like images and videos. But of course, we can see that those things are never going to directly pertain to all of the language that this system ends up using. And so where do we get our understanding of things like democracy and all those other things? And I suppose they come about through our involvement in a society of language users and the fact that we can write things down, we go to school, we read books and all of that. But it feels to me like if we use human understanding as a guide, at least, that understanding the concrete things is kind of a necessary part of understanding the abstract thing. That's kind of what I was trying to demonstrate and show in my PhD, but admittedly without the sort of large scale corpora and big models that we have today. So it was kind of a much more small scale analysis around questions like that.
Awesome. So in the paper, there's this idea that between abstract concepts, the relation might be more symmetric, and between concrete, it might be more asymmetric. And you also mentioned that this could be measured in sort of priming tasks or free association tasks. And could you tell us a bit more about that?
Wow. Yeah. Okay. So this was the very first paper, pretty much the very first paper that I published, certainly the first paper that I wrote in a journal. Yeah. So there had been various theories about how we represent abstract concepts and how we represent concrete concepts. Like this is cognitively, right, in some sort of mental model. Loosely speaking, there was a theory that concrete representations are sort of feature based. And what that means is that, so if we think about a cup, there's some inherent kind of intrinsic properties of the cup that come together to contribute to our mental representations of cups. So it could be things like it's shiny because it's made out of china, and it's got this handle on the side which allows us to pick it up. It's probably got some sort of cylindrical or curved property. It has the possibility of being many different colors, but there's probably a bias towards it being, say, white. This is not saying that it's a feature-based representation. It's not saying that there are sort of necessary and sufficient conditions for being a cup, but simply rather that maybe some loose probabilistic distribution over some expected properties contributes to us eventually deciding that we're recognizing something as a cup. Now, when it comes to abstract concepts, we can't do that, right? Because we can't perceive the intrinsic features. And so there's a theory which says that in actual fact, an abstract concept is defined in terms of its role in some wider structure. So basically it's defined in terms of the place it occupies and its relationship between all the other abstract concepts in our big mental network of concepts. And that's kind of a very different conceptual representation, because that concept then doesn't have intrinsic features. The existence of intrinsic features, if you go back to read the beautiful work there's a guy called Amos Tversky who actually got the Nobel Prize in economics with Daniel Kahneman. He was actually first and foremost a kind of cognitive psychologist. And he has this beautiful work called Features of Similarity, where he points out that if a concept has a kind of feature or property-based representation, then we should expect various asymmetries in the way people understand it. So I won't go into the details of why. But what I mean by asymmetries is that people's understanding of concepts might be asymmetric if the example he uses in the paper is things like people are more likely to sign up to the idea that North Korea is similar to China than they are to sign up to the idea that China is similar to North Korea. And you might have an intuition for why that is, but it's probably to do with the asymmetry that they perceive in terms of the power structures or the populations or some different aspects of those individual countries. And Tversky pointed out that these sorts of asymmetries are much more likely to be observed in feature-based representations rather than in the kind of structural, relational representation that I proposed could explain how we understand abstract concepts. So if that's the case, we ought to expect more asymmetry in our understanding of concrete concepts than abstract concepts. And so in this paper, what we did was like a really large scale analysis of other people's data where they'd already got loads of different words and tried to measure how similar one of them was to the other. And so we could take that data and measure the degree of asymmetry. And we found indeed that there was much more asymmetry. Well, when I say much more, I mean statistically significantly more asymmetry among the concrete words or pairs of concrete concepts than there was between pairs of abstract concepts. And so this was kind of like a small bit of empirical evidence which supported the mental theory that concrete concepts are represented according to features, whereas abstract concepts are represented more in terms of their relationship to other concepts and their position in some large structural world model of our knowledge.
That sounds really interesting. I'll get back to that when we talk about analogies, but let's talk about language models and transformers. So before we had transformers, most language models consisted of recurrent neural networks, RNNs, or long short-term memory, LSTMs. And could you tell us a bit about this history of how we got from RNNs to LSTMs to transformers now, and maybe also what these three terms mean?
Okay, yeah, so that's quite a lot to cover, but I'll definitely have a go. So I guess the first thing to say is when it comes to modeling language with neural networks, I think one very important, but not necessarily the most scientifically interesting challenge, but one very important challenge is how to cope with variable length inputs, right? So if you're modeling images, you might assume that you could just chop all the images to the same size, pump them into a network, and then make a prediction, right? And that's kind of easy. But if you're modeling sentences, you don't know how many words that sentence is going to be. And as we know, there could be incredibly long sentences and very short sentences. And so it's not clear what sort of architecture we need to be able to cope with that difference in the input. And so one attempt, so in the early 2000s, Yoshua Bengio developed, one of the first neural networks which was capable of processing sort of natural language that you might take from the internet. And the way he handled this problem of variable sentence lengths was simply to chop everything off at 4. So this model was a model which had an input space of 4 words, and then it would first model 4 words and then move one step to the right and model the next 4 words, and move one step to the right and model the next 4 words, etc., etc. In doing that, it would make a prediction about what it thought the subsequent word ought to be. Now, as you can probably imagine, although it was a really amazing piece of work, it's quite limited because this model has no ability to make connection between anything other than 4 consecutive words. And when predicting the subsequent word, it's very often the case that there are these long-term dependencies where we actually need information from a few words prior to the 4 previous words in order to make the best prediction about the next word. About 10 years later, when technology and sort of computer capacity and even like things like GPUs had started to be used for these sorts of work, there was more capacity in models, and people started to think, well, how can we go from the model that Yoshua built to kind of relax this limitation that it can only deal with 4 words at a time? The solution they came up with was to use a type of model which had actually been developed by psychologists in the late 80s called a recurrent neural network. Back then, it had only been used with very toy data, although there was actually some nice applications, more increasingly nice applications of it in things like speech, I think, throughout the 90s. But then by this time, it felt like the right time to kind of take what Yoshua had done with this 4-word model, try to attempt to apply a recurrent neural network. And a recurrent neural network has a very different architecture. So with a recurrent neural network, you have a sort of chunk of weights. So this is a chunk of sort of computational capacity in the model, which is going to be reapplied many, many times as you're consecutively reading the words in the input. So I'll read the first word in a sentence, then I'll apply these weights, this computational kind of chunking, this computational function, which I'm also going to learn. I'm going to apply that to the first word. Then I'm going to sort of incorporate the second word. Then I'm going to apply this computational function again, which I'm also learning. I'm going to incorporate the third word. Then I'm going to apply this same computational function again. So I can keep applying this matrix of weights to words as they're coming in. And so each time I end up with an activation, which we could think of as a state, I'm going to then add to the state the subsequent word and keep applying it. Conditioned on the state, I'm going to make a prediction about what the subsequent word ought to be at each time step. So I give myself many prediction problems, but in theory, when I'm predicting the 100th word, this model in theory has the possibility of incorporating information from the first word, right? Because in some sort of computational graph, I've connected the first word with the 100th word, all through the reapplication of this update function, which I'm learning a matrix for. So that's how recurrent neural networks work. And in theory, the recurrent network could account for dependencies in language that are arbitrarily long, right? So if I start a story talking about some topic, and then I later go and talk about a different topic, and then I start talking about the first topic again, potentially I could use that knowledge that I gained at the very start of the book to help me make predictions about subsequent words now. That's in theory what we can do with a recurrent network. But in practice, there's a big problem, which is that this reapplication of the same set of weights, the same matrix, makes it very hard to train these models. And in particular, it makes it hard for them to pick up on long-term dependencies. And this is just a mathematical fact, because what we're doing when we update this model is we're doing something called backpropagation through time. So you can imagine if you're applying weights, the same weights multiple times, then a small change to one of those weights gets massively magnified such that it actually ends up having a really big effect on the ultimate predictions of the model, particularly if you enroll it for like 100 time steps. So it's very unstable to train. And this happens when you update a weight, but it also happens with the signal we use to know how to update the weights. So that's known as the gradients. And the gradients can multiply. And if the gradients are bigger than 1, they're just going to go up and up and up and up and up and get enormous by the time they get back to the original first word in the corpus. And if the gradients are below 1, they're going to get smaller and smaller and smaller. They'll be non-existent by the time you get to the first word in the corpus. So all this means that using the techniques that we use to train neural networks, backpropagation, it's very hard to train recurrent neural networks. See the importance of relating the first word in a corpus with the 100th word in a corpus, right? It's really hard. And so LSTM was kind of an extension of recurrent networks to try and help get around this problem. And for a while, using LSTMs was a big step forward over using recurrent neural networks. But then in the last sort of 5 years, the transformer has developed, and that's kind of like really helped to solve a lot of these problems that I just described about vanishing or exploding gradients and relating together things in language which might be separated by a large number of tokens in terms of the ordering of the words in text. I'll just say a bit about how the transformer works. So the transformer is actually a bit more like that original model I told you about from Joshua, where basically it processed just 4 words at a time. So there's no recurrence, or at least there isn't recurrence in a simple way, like I just described in the recurrent neural network. But the difference with the transformer is because computers have much more capacity now, you can actually take that 4-word window that Joshua used, and you can make it something like 2,000 words, right? So we can make the window much bigger. So that already means that when we put one of these networks on text, it has a chance to connect words that are 200 places apart in some corpus. But also there's an even more important thing here, which is that unlike the recurrent neural network, it's not hard for the model to learn to connect them. In actual fact, it's easy for a transformer to learn to connect 2 consecutive words as it is for a transformer to learn to connect a word and then a different word, 1,999 words later in text. So the way that the transformer works, it's entirely symmetric with respect to the inputs, apart from a small position embedding trick, which allows the model to be aware of the ordering of the words. And because of that symmetry, it's equally easy for the model to recall things which are, 1,800 words ago, as it is for them to recall the last word that it's just heard. And it turns out that that capacity is really, giving a model that ability is actually really good when it comes to modeling language. And that might be surprising because we all know that in actual fact, the words that are close to a given word in text ought to be much more relevant to that word than the words that are a long way away, right? It's just a fact that the stuff I'm talking about now has a very high probability of being related to the stuff I was talking about 3 seconds ago, but it doesn't have a very high probability of being related to the stuff I was talking about 10 minutes ago. So given that language has that undeniable structure, why is it the case that a model which encodes that bias or which has a bias towards favoring relationships between subsequent words, why is it the case that that model ends up being worse at modeling language than the model which has no such bias? And I think this is a really important lesson about the role of the potential pitfalls of inductive biases. I think it's important because the sort of pattern I told you in language, which everyone knows, which is the fact that things which happen nearby in time are more likely to be connected in terms of, their meaning or their relevance to each other. That fact about language is so obvious to a statistical learner that it's really easy for both LSTMs and transformers to learn about it. There's just so much signal in the data telling it that. But what's not easy is these cases where it's important to know exactly what I was talking about 3 minutes ago in order to make sense of the world now. Those are actually the cases which have led to a huge improvement in language modeling since the transformer was developed. Because there are actually a lot of times in language when I'm using language, but what I want to do is kind of like think, I've been in this situation before. I'm just going to do exactly what I did then. So I want to be able to kind of travel back in time to some point in the past, grab that information and use it right now. Or potentially I'm starting to tell you a story, then I'll tell you about something else, then I'll go back to the original story. And when that happens, it doesn't happen very often, but when that does happen, a transformer gets it right and potentially an LSTM gets it wrong. And it's that ability to more easily learn the difficult stuff that makes a transformer better. And because it doesn't have an inductive bias towards the obvious stuff, that's not a problem because that stuff is obvious and statistical learners pick it up anyway. So I think there's a really interesting lesson there about the potential pitfalls of encoding inductive biases in our models in a careless way. So I think we need to think very carefully before prescribing the encoding of more inductive biases as the right way forward for producing better models.
So you just mentioned the words prediction and time, and that's actually my next 2 headers for the next topic, so that's great. So in my last episode, I talked with Mark Spurek about predictive coding, which is a neuroscience idea that the main task the brain is trying to solve is predicting the body's actions and the sensory world. And in a second, I want to ask you about this idea of embodied prediction, but going back to the large language models you just mentioned, and some examples might be, GPT-3, BERT, Gopher. As you mentioned, essentially what they're doing is trying to predict the next word or the next sentence based off the previous words and sentences. Why is prediction so important for these models to become good language models?
Yeah. So in your previous podcast, sounds like you talked about the sort of importance for prediction in learning in animals, right? Or in humans. And I think there's a lot of evidence that things like predictive coding and predictive learning are happening all the time in those cases. And I think about why that might be. It's kind of a no-brainer, right? Prediction is always possible. It's free in the sense that you don't need someone there telling you some useful information or giving you a label. You can just set yourself a challenge of guessing what's next. And then if what's next isn't what you thought would be next, you can kind of observe that and say, okay, well, I'm going to learn something from my failure to predict that, right? So it's like free learning. And it happens to have the property as well that the more you understand about the world, often the better you are going to be at doing that. So given that it has that property, doing it can in some sense be a catalyst for you learning about how the world works, what to expect, where things are, and all that. So that I think is why predictive prediction is really powerful, right? But of course, in animals and humans, people who know about learning would point out that there's definitely more to learning than prediction. And there can be retrodiction. So, it's also kind of free, provided you've got a reasonable memory to set yourself the challenge of predicting your memories given what you see now. And then there's also supervised learning, right? So we do bump into people who tell us important stuff or tell us why we went wrong. We could get asked a question and make a prediction and then get told that it was wrong and what the right answer was. And in fact, a lot of that stuff happens in schools. So that's kind of like supervised learning. And then there's also reinforcement learning, right? We can set ourselves challenges or we can be set challenges. And if we get them right, we can be rewarded. And if we get them wrong, we can be punished. So all of those kind of combine. But there's probably always prediction, because while we're doing any of those things, why not just do prediction as well? It's free. So similarly, we can perhaps see that like the prediction in models like GPT-3 or the retrodiction in models like BERT, it's kind of like the workhorse of learning. It should always be going on. It can happen all the time and it's critical. But if we want to create a model that has agency or does something for us or has some of the properties of animals and humans, then we may also need to combine that type of learning with things like supervised learning, like humans get in school, and reinforcement learning, people trying stuff out, seeing where they went wrong, and getting some signal about what was right or what was wrong. And indeed, this conflation of various ways of learning, which is kind of like what's happening in humans and animals, I guess, is precisely what the NLP community seems to have kind of like converged on, right? So now that there's work on retrieval models, there's work on GPT-3 and BERT as a sort of pre-training phase. And then once we've trained those big models, we tune them with supervised learning or reinforcement learning. And most work in NLP, I think, will probably start from one of these models, which has had a lot of pre-training through this notion of prediction. Now, of course, in animals, it all happens synchronously. So prediction happens at the same time as supervised learning, which can happen at the same time as reinforcement learning. And in NLP, often these things are in stages, but I think that's just a practical detail. It's just because it's easier to take a model off the shelf that's already been pre-trained by Google's TPUs or OpenAI's TPUs, and then to use that to go and actually do the research of making it be useful or making it behave with agency or in some sort of way which it provides a useful technology for different people.
Yeah, that was an awesome overview of a prediction. So the other heading was time, and there's this famous paper by Jeff Elman, she wrote in 1990, called Finding Structure in Time. And in the paper, he sort of explains that neural networks, when they try to learn syntactic or semantic features of words, they need to form these internal representations that make sense of the temporal structure between the words. And he also explains how kind of recurrence, prediction error, and memory, which we sort of just mentioned a bit, all fit into this. And I know you presented a talk at a symposium in memory of him. So I was wondering whether you could maybe say a bit more about his paper and also maybe how his work might have inspired some of your work.
Yeah, thanks. So sadly, I never met Jeff Elman, but I do work closely with Jay McClelland, who was, I think, great friends and collaborator with Jeff Elman. I think that Finding Structure in Time is maybe one of the most important papers in the history of cognitive science or psychology. And my evidence for that is maybe precisely its importance to modern AI, AGI, and language modeling that we're seeing now. The paper itself is quite simple. So Jeff, like all good papers, I guess. So Jeff develops a small recurrent neural network. So this is exactly the type of network that I was describing when I described how recurrent networks were used for language modeling around about 2010. But this was in the early 90s and the late 80s. So Jeff had just had a very small version of such a recurrent network with a small number of units. So it takes some input and then it applies a transition function, a matrix of weights to that input. and a nonlinearity, and then combines it with the input at the next step. And then that process continues, and that process continues. And at each time step, or potentially only at certain time steps, the model also, conditioned on the state of that model, it has to make a prediction about the output. And then to train it based on the error of that prediction, it can be backpropagated through those weights multiple times, through the transition weights and into the inputs in order to update those weights. That's the sort of network that Elman presented in this paper. But the important thing about the paper is not the network itself, but it's what the sort of scientific demonstrations that Elman tried to show with the network. So in particular, what he wanted to show was that although there's no sort of structure in this model relating to particular patterns that we might expect in natural phenomena, the model has the ability to infer those patterns. Those patterns can kind of emerge in the state of the model as it learns. So one sort of set of patterns is the way that letters cluster together into words in text. So Elman wanted to see whether or not this ability to sort of pick out the words from a stream of letters might emerge in this model. And so he trained it by training it on the sequence of letters in some English. So just found some English text and gave it each of the letters one by one, but he didn't give it the white spaces. And after a certain amount of training of the network, he considered it trained, and then he started to analyze its prediction errors. And he found that the model had much bigger prediction errors when predicting the first letter of a word. Some test corpus, he again fed it letters by letters, and he found that the prediction errors were highest when the model was having to predict the first letter of a word. Subsequently, its prediction errors went down a lot. So by looking at the prediction errors, you could see where the word boundaries ought to be. And he concluded that this model was able to kind of use the statistical transition probabilities between letters to slowly acquire a sensitivity to where word boundaries ought to be without any other sort of signal. So even a baby learning where word boundaries need to be in speech probably also gets some signal around how long there is in terms of pauses between particular words. It's not a very clear signal, but it's definitely some signal. This model didn't even have that, right? It didn't have any indication of where the white spaces should be. It just inferred, after reading lots of different, getting experience of the words of the language, what different patterns of letters might normally occur towards the end of a word, and then what sort of patterns of letters might normally occur at the start. And it had kind of developed a sensitivity to finding those spaces. And then another experiment he did was more around sort of like being able to infer the semantic clusterings of the world just through language. So in order to do this, it was not possible to train on large amounts of natural text. Jeff created a sort of synthetic language. So the synthetic language had a set of nouns. So it might have sets of nouns like fruits. It might have sets of nouns like tools. It might have sets of nouns like agents. So agent would be a person or an animal. And then it had a few verbs, right? So it would have a verb like eat, or it would have a verb like runs, or it would have a verb like, cuts. And of course, as we know from our understanding of the world, only an agent can run, right? So a fruit can't run. Only an animal or a human can run. So that defines some constraints on this language. So sentences could only involve one of the agent nouns going with the verb cut or run, and then it could involve only one of the fruit like nouns could go with the verb to eat and things like that, right? So there was some natural constraints in the language. And then he presented the network with sentences generated by this language, generated according to these constraints. So sentences which made sense in this language. So the model was modeling these sentences one word at a time, just predicting the next word. At that point, once it was trained on the language, he looked at all of the activation states of a model on the test corpus, and he clustered them according to some naive clustering algorithm like k-means or something like that. And what he found was that the representations corresponding to the fruits clustered in one place, and the representations corresponding to the tools clustered in a different place, and the representations corresponding to the agents clustered in a different place. This kind of shows that the model had inferred these semantic categories just by the patterns of the way they interrelate with each other in text. Both of these experiments show that at the time, the kind of the argument I think Elman was trying to make was that these models don't need to have these sorts of structures about the world. The fact that fruits are different from agents, or the fact that, where the explicit word boundaries come in text. These models don't need to have that hard-coded inside their mechanisms in order to be able to infer it naturally from data. And so it told a bit of a story about how those sorts of sensibilities and concepts might emerge in human learners without, say, pre-programmed or innate machinery. And I think it also indicated sort of how hard it is to separate the influence of, say, things like syntax and semantics when modeling language, and how like even semantic properties of words might be inferred from kind of the distributional patterns of the way words operate and how they participate in arrangements with other words. So in that sense, if you just think about those kind of notions that Elman was trying to put forward, they're just absolutely everywhere when we consider how people do modern AI. And so I think at the time it was very controversial what Elman was saying, but if we just look in some sort of dispassionate way at what's going on at the moment, it seems very much like Elman's been proved almost entirely correct.
Yeah. So you just mentioned Sutasi was talking about the word boundary clustering or semantic boundaries. And at the end of the paper, there's this quote: "The representation of time and memory is highly task dependent." And I was wondering whether this observation, whether you have noticed that in some of your own experiments, or whether do you have anything to say about that?
Yeah, I'm not an expert in the philosophy of time and things like that, but I do know that time is something which, as biological learners, we are constantly exposed to, and it's kind of like totally shaping how we learn, right? Because for example, the notion of prediction only means anything because of time and the fact that we can't know the future, but we can potentially know all of the past. And we can use that sort of asymmetry in knowledge in order to set up an interesting learning objective for ourselves. So I don't really understand what Elman was referring to when he talked about time having different meanings in different contexts. But certainly, I think, one interesting connection here is that now a lot of my work and the work of our team focuses on an agent where there's this sort of like discrete notion of time every time step. And maybe there might be something like a language event or something like a physical event that the agent observes. And that might happen only every 30 or 40 time steps. And then there's the notion of time in language, where if we just think about text, clearly this is a representation of something that someone might have said at some time. And so therefore we might think of like the word on the left as being before in time, the word on the right. And that's indeed how we set about modeling a lot of these, a lot of text. And that's how GPT-3 models text and treating that text as having a bit of time to it, even though, of course, we could just put all of the text in backwards or all at the same time. By treating it as if there is some time there, I think that there are some certain like emergent properties that come out of it. And indeed, those emergent properties seem desirable to us, probably because we understand the world with that kind of temporal aspect. And ultimately, what we think of as being a good language model is giving behaviors that seem natural to us. And they probably seem natural to us because the language model was kind of biased with this strong constraint that you can't really know the future. If you do want to know the future, you have to wait for it to come to you. Yeah. So if that means anything, that would be my understanding of maybe what Elman was suggesting. But it's a philosophical topic that I'm not very good on. So I think I'll probably stop there.
Yeah, the point about the agents experiencing the world at different times. I want to get back to that when we talk about your work with 3D simulations, because I found it was really interesting. But let's now get onto you have a 2019 paper on analogies, and you mentioned the work of Dietrich Gärtner, who came up with structure mapping theory. And in this theory, there's this idea that there's a difference between analogy and similarity. Whilst analogy is about what relations objects share, similarity is about which attributes they share. And do you have maybe an example to showcase this difference between analogy and similarity?
Yeah, okay, so that's a bit of a change of tack, but I do think that's a great way of putting it, that things are similar if they share lots of attributes, and maybe more analogous if they if they have lots of relations in common, or perhaps, if they have some sort of similar structure in the way that different components within them and the things they relate to can be aligned. So in the paper, I think we used this motivating example. I don't know if it's the perfect example. The analogy between the sea, which is something we can easily perceive here, we could see it, with sound, which we can't see. We can see the sea, but we can't see sound. And the Romans used an analogy between these two domains to improve their understanding of sound. So they observed with their eyes that sea can like bounce off walls, or that waves in the sea can kind of have a certain periodicity. And they used that knowledge. They sort of then intuited the potential connection with sound. And they used that potential connection to make predictions about sound, which actually then they could test, and they usually were confirmed. So in some sense, they were making an analogy between C and the sound. And then they were saying, okay, which aspects of the C do we think might be shared with sound and in what way? And that process of kind of connecting the two domains could be thought of as like a prototypical example of analogy making. And the important fact here is that there's no perceptual similarities between sound and the C. Or you can't see sounds. Sounds aren't wet. They're not blue. So we probably wouldn't say that sound and the sea are similar, but their structure or relational similarity in the way that they kind of interact with other things and in the way in which they kind of inhabit a particular system. And so we would say they're analogous. And I think that example and the fact that the Romans were able to use that to actually better understand sound, that also shows the power of analogy in potentially explaining, inferring causes, and generally being creative and understanding the world.
Yeah, I love that you went back to the Romans. In my last episode with Mark Spivak, we went back to the Greeks about like group cognition. So it's too fitting. But so in the paper, you talk about how you can maybe implement this in a model and we could then solve analogies. And sort of what you point out that is it's not necessarily the architecture that's important for a model, but in the way of which data and how the data is represented to the model. And I was wondering whether you could elaborate on that.
Yeah, I'll just quickly say that the example from the Romans was in the paper, we just sort of lifted that example from people who are more expert in analogies than we are, right? So like Keith Holyoake, I think. So I don't want to claim it was my classical, my knowledge of the classics, which enabled me to make that connection. It was just reading some psychology papers, but I think it's a nice example. In terms of your question about what we found in that paper and the importance of the training data, Dedre's structure mapping theory tries to sort of propose a cognitive process which allows us to make analogies. In the paper, we don't try and argue in favor or against that particular theory. In fact, we don't really want to do cognitive science in some sense. We don't want to try and understand exactly the mental processes which go on behind analogy. But we are interested in how a neural network could learn analogy using gradient descent. So we set up these little visual tasks. We created, it's little graphics like stars and circles and lines, and it's all black and white. And we created 7 domains. So one domain might be like triangles, the other domain might be circles. And these circles can be various sizes, various different colors and things. So we've got some large space of different domains. And then we had like 4 or 5 abstract rules. So they could be things like X or and, or the notion of increasing or the notion of decreasing. So we had these abstract rules and we had different domains. And in theory, each of the rules could be applied to each of the domains. And then we would show an example of a rule in a given domain, and then we would show a different domain and ask the network to apply the same rule to that domain to complete a pattern. So the idea here was if the network is able to infer the rule by observing some changes, so infer some structure from one domain, and then take that structure and apply it to a new domain, then in some sense it would be solving a problem by using analogy. And we trained a recurrent network actually, so just very much similar to the one I described Jeff Elman having invented. But we trained it, unlike Elman who just put symbols, who put words directly into these models as symbols, we trained it on pixels. So we trained it to actually see the patterns. And that allows it to do more generalization, right? Because in some sense, this model, if there was a similarity between triangles and circles, the model would be able to see that, right? If we just chop triangles and circles up into different symbols and give it to the model, it's going to think of them as just maximally different things. But in this case, the model could see perceptual similarities, but it also had to infer these structural similarities. And we found that these recurrent networks were actually able to do this, but we had to obviously train them on loads of analogies and then test them on some held out analogies. And they did really well. They were able to sort of infer known rules from known domains and apply them to completely new domains with some above chance success. So it was really evidence of having acquired an ability to make creative analogies. Having said that, there's some important caveats. So one is that humans don't learn to make analogies by like practicing hundreds of thousands of analogy problems. Whereas that's what we had to do with this network, right? We had to train it on analogy problems. So that's not very biologically or ecologically realistic. But the other important thing, and this is the point about the data being important, was that these are actually multiple choice analogy problems that we trained the network on. And what we found was critical for the network to learn to do the analogy was to give it the right multiple choice answers. So, I mean, the right answer is always there in these problems. But the critical thing was that the wrong answers were the right type of wrong answers. And in particular, if you just randomly choose wrong answers, then the network doesn't learn to pick out the structure very well or generalize very well. You have to be clever with your wrong answers such that they're designed to kind of teach the network something. And what they're designed to teach the network is like, they kind of represent obvious mistakes or obvious incorrect ways of solving the problem. And then there's this one correct way. And if you do that when you're training the network, it learns to pick out the right structure. And you actually see that because it learns to perform much better on these held out test sets than it would do if you just chose random confounders for your incorrect answers. So I think there's a nice analogy with teaching and education, because I don't know if you have a sense, but in classrooms, I think good teachers often, one way in which they can be very effective at teaching a new concept is to pose a multiple choice question, or to raise the common misunderstandings or common pitfalls with a new concept. So it's almost the best way to ensure that you really understand something, and I'm really going to teach you well, is to highlight the important decision boundary by telling you, okay, not only is the answer to this question, King James, but it's not King John, because you might have thought it would be, but in actual fact, it's an easy mistake to make, but in actual fact, no. And, it's also not Queen Elizabeth because, some other reason. And so if you can kind of contrast the right answer with like plausible, but incorrect wrong answers, then the network gets the principle that you're trying to teach it much more effectively.
Yeah, I think with neural networks, there's often that problem that they can find backdoor answers, and that with your wrong answers, that you focus on the fact that it's not just a domain matching thing where you just have wrong answers from different domains and then the network learns to classify the domains in some sort of sense, but it's about then having maybe the wrong answers from the same sort of matching domain, so it has to look at the analogous thing, if that makes sense.
Exactly. Yeah, that's a really perfect description. And you're right. For a different class of models, this might not be necessary because they wouldn't even entertain the wrong hypothesis. But neural networks entertain every hypothesis. And so you do have to be careful or clever in how you kind of educate them.
All right. So let's talk about grounded language learning in 3D simulations. This really fits the theme of the podcast. So that's great. So basically what you're doing is you're studying grounded language by putting agents in 3D virtual environments. And you're not just giving them language, but also visual input. So it's multimodal. And could you tell us a bit about the motivation of using 3D simulations and maybe some of the tasks that you make these agents do?
Yeah, so I think the motivation comes from like something I mentioned before about how humans might come to understand the abstract world as well as the concrete world. I think almost as a sort of substrate or a precursor to our understanding of complex abstract things, mathematics or social interactions or democracy or war and things like that. I think a lot of our understanding is built on a reasonable understanding of the physical world. Indeed, this is a point that a lot of cognitive linguists try to make. So very closely related to the notion of analogy is the notion of metaphor. And George Lakoff has this very famous book, Metaphors We Live By, where he points out that almost all language can be considered to some extent metaphorical. Right? So if I say, a large number, I don't really mean that there's a large number like an enormous 8 or something, which is towering over me. But if I said a large building, that could be considered quite concrete. And maybe I literally do mean that it occupies more space in my field of vision. More pixels are taken up by this building than the building next to it. So if I think of the building example as like almost the concrete meaning of large, and then the number example as being somewhat more abstract, I'm sort of extending that understanding of the concrete to a more abstract system, which is the number system. And then we could talk about a large issue or a large discussion or a large problem. And in those cases, it's even less physical, right? It's really hard to imagine what that has to do with space at all. But I guess the hypothesis and Lakoff's evidence from metaphors is intended to suggest that we're kind of taking our knowledge of the easy cases, the concrete cases, where we first acquire a notion of large, and we're kind of repurposing that knowledge to usefully talk about things which are not immediately in front of us. And that ability, I think, underlines a lot of humans' cognition. And I wouldn't be surprised if it being a sort of key part of why we are clever. And if that's true, then we do need a way of our AI systems understanding the physical world as well as understanding language. And to understand the physical world, that means being able to observe it. So being able to see what two buildings are like and how they're different in size. But I think it also means being able to interact with it. It means being able to sort of throw stuff around and see what happens and make a little experiment where you pile the blocks up and they fall over and putting things in other things and all of that. And so that's why we tried to start thinking about the problem of language understanding in machines by giving agents access to a physical world. But of course, it's not a real physical world, it's a 3D simulation. And the reason for that is mostly pragmatic, right? Like, I don't believe that this simulation is more interesting than the real world. It's just that it's very hard to do the sort of research into general intelligence and cognition in the real world, in a robotics setting. I don't think that will be true forever. And I think it's increasingly less the case. But for now, we've done a lot of work in 3D simulations. And these are worlds where the agent can pick up objects, they can throw them around. They're not sort of totally photorealistic, but they're realistic enough that if you looked at the world, you'd see that there's a cup, there's a table. You'd understand what's above what's bigger than what. You can basically understand what's going on. You probably don't even need any experience of 3D computer games, and you'd be able to look at this and see what's going on. It's like a caricature of reality, but it has important aspects of reality. It has some physics, simulated physics. So things kind of like bump into each other and fall off things and all of that. It's also experienced by the agent from a first-person perspective. So the agent can only see what its eyes allow it to see given where it is in the world. And it can then move its field of view looking up, down, left, and right. And I think that has some important implications for what it actually learns about the world.
Right. Since you just mentioned the George Lakoff book, I thought on your website, I thought I mentioned this as well. On your website, you link to a Douglas Hofstadter talk about analogy, which I think relates to all of this. And I really enjoyed listening to that talk, so I can recommend it to anyone listening. Let's talk about, I want to go back to time, actually. So there's this nice quote. You mentioned a Zoom talk with the UCL Dark Lab. And the quote is, memory is harder for an embodied agent in a useful way. And I think the idea behind that was that if you have an embodied agent in a 3D simulation, when it does object recognition, it gets several timestamps of several image frames of an object. So it can look at it from several angles for several timestamps. Whereas, let's say if there was like a classifier that only gets one image, it only has that one snapshot, that one timestamp. And you said that can be useful for memory. So could you tell us a bit about this intuition?
Yeah, I mean, so if you think about how we experience the visual world, it's active perception. So we decide what we're looking at. And not only that, but we never look at just an instant snapshot of an object. Well, we rarely do. Maybe we look through some photographs that are on the internet. But while we're moving around our physical environment, we're looking at objects from all different angles. And our input is highly correlated. The input we get at the next time step is very likely to be very similar to the input we got at the previous time step. And this definitely has implications for how we can learn and understand about the world. So I think, for example, we never see a single view of an object. We always see lots of different views. And that can tell us a lot about the object, a lot more about the object than if we just had one view. And I think this is particularly important for young infants. And so there's this beautiful work by Linda Smith where her lab, they try and quantify exactly what babies see by putting head cameras on them with the consent of the parents, I should add. Kind of like watching those videos and analyzing the types of data that they see. And what's really critical here is that they see a lot of toys, but they see most toys very rarely and some toys incredibly frequently. And those toys are often interacted with. They're picked up, they're moved around in the field of view. And Linda's hypothesis is that this is kind of critical for a child learning some sort of abstract general notion of what an object is. And as a consequence of this early experience, the child's neural network is then sort of much better set up to learn about more and more objects. And it may be that real sort of crash course in a few objects that the child is getting really expert on sets it up for then quickly learning about many, many objects. And you start to see these sorts of curves where the learning about objects just sort of like somehow accelerates rapidly. And this is actually kind of like a language explosion where the child then can suddenly talk about thousands of words rather than just 5 or 6 within the space of a few months. So Linda's hypothesis is that this distribution of data, which almost all children potentially have, can be quite important. Now, I don't think she would want to argue that it's the same for all children across the world. And in fact, she's done some of this work in very different cultures in other countries. But there seem to be clear similarities between the distribution of experience in those cases. So anyway, in our 3D simulation, just by virtue of being an agent in the world, our agents are kind of getting experience a bit like that, because they're picking up objects, they're looking at them, and then they're getting many, many hundreds of time steps of frames, which focusing on a particular object. So it's an attempt to understand in neural networks the effects of having that experience and how that could be beneficial. And we've already seen loads of cases in which it seems like, compared to an agent which just gets a uniform distribution of images from a single viewpoint, an agent which experiences the world by moving around can do things differently and potentially, I wouldn't say better, but certainly more similarly to how humans seem to do them. So for example, we've shown that an agent which moves around the world and learns about objects in this way can generalize to unfamiliar combinations of objects better than an agent which just gets individual images. And in fact, if an agent has to pick up objects and learn about them in this way, it can generalize to doing interesting new things with familiar objects much more effectively than an agent which doesn't get the same amount of experience of each of these objects. This kind of suggests that it's kind of building a really strong representation of a few objects, which underlines a lot of humans' ability to generalize to understanding new objects. And maybe that understanding comes from this really concentrated experience, picking up objects, moving them around, seeing them from all different angles that we get in our initial training. And if that's the case, maybe a lot could be gained by training neural network models to understand the world in this sort of simulated way. That's kind of the hypothesis we're working with in this research.
Yeah, it's interesting. It gives that whole, if a child has like a favorite toy, it gives that a whole new angle of not just, well, that's emotionally important, but also, well, cognitively important. So you mentioned that one of the benefits of then like learning, getting these different snapshots is that you can maybe recognize unfamiliar objects, or you can interact with familiar objects in new ways. And I think for that, memory is a really important thing. And it's also some of the challenges in some of the models. And I thought you had this interesting point about the distribution of different data types of language and vision, in the sense that language is quite sharp and discrete. Either I say something or not, whilst vision is this continuous visual input. And arguably, there's a lot more visual data because it happens all the time. And you make this point that, well, maybe the language input at timestamp X maybe sort of structures the way the visual input is remembered at the same time point X, and then maybe then the visual input is made more salient, and that's maybe important for the memory of the model, and then these applications I just mentioned. And maybe you have a bit more to say about that.
Yeah, well, I don't have a lot more to say because that was like a really clear explanation, and I totally agree. It's like you've said it better than I could. But I do think there's something here. So one of the beauties of neural networks as models of cognition is that they allow for different information types to interact. And that's super cool. We can just take language data and mix it with vision data in some way. And we can build models that account for the interaction between vision and language. And that's actually quite hard to do with other paradigms because, the type of data wasn't just some distributed representation. And so how to mix them together in an elegant way was not clear. And of course, I think I've hopefully tried to explain that a lot of cognition is about the interaction between loads of disparate different data sources and making sense of that. So I think that's the ability to mix stuff together is a real advantage of neural networks. But I think in this work, we tried to demonstrate that there's also some advantage to be had for not mixing everything together. and the reason is, so what I mean by that is that a lot of multimodal models, they'll just merge vision and language into some shared dense representation and then do something. And that's cool because it allows you to combine the information in the vision and the information in the language. There are advantages also by keeping this information separate, but potentially aligned. If I've heard and seen something at the same time, I know that this information should go together in some sense, but do I really want to merge it together into a big shared representation? Potentially in the separation, there might exist useful information because we've got two very different distributions of data, as you said, actually. So there's vision, which is always there, which is highly correlated one step to the next. And, so picking out the modes in that distribution might be quite difficult, picking out the important events. But then if we keep that separate to language, but aligned with language data, picking out the modes, the important events, is going to be a lot easier because language is not always there. It comes and goes. And indeed, it's sort of a lower bandwidth signal. So working out whether something's important from the language could be easier. And so if we keep them separate, we can then, in a memory system, we can then do interesting things. We can use the language modality for retrieval. So basically, I want to look back in my memory and I want to say, well, when did something important happen? Or I need to remember something about cats because somebody's just said the word cat. How can I find something in the past that's relevant to cats? And all I have to do is kind of match the word I've just heard to the language in the past and the reference to cat in the past. But because I've kept the language and vision data separate, I can then I can look up according to the language and return the relevant experience that I experienced visually at the same time. And this becomes quite a powerful mechanism. If I'd have merged together language and vision into some dense representation in my memory, I'd had to do some sort of quite complex pattern matching inference mechanism on my own memory in order to find the bit amongst all of the stuff mushed together, to find the bit that's relevant to cats. It could be quite difficult. I need to do almost some interpretation of dense vectors, whereas if I'm looking up just for the word cat, it's, or maybe I'm looking, maybe the word tiger, but I'm just looking up in a word embedding space, it could be a lot easier to find the right information. And then I can send back to my decision-making part of my network. I can send back the corresponding visual experience as well as the language experience in order to combine them and make a decision. So that was just one example in an agent where we thought keeping distinct modality representations of the same event separate in memory actually had some advantages. And this corresponds to this dual coding theory from a psychological theory of how information is stored in humans. And so that was just a kind of a nice connection, very loose connection. We're definitely not claiming to have proven the theory or anything like that, but it was nice to make that connection with psychology and what our agents were doing.
Yeah, I have to say I'm totally promoting my other episodes in totally arbitrary ways, because you just mentioned cats, and somehow when I talked with Mark Spurbeck in the last episodes, we kept talking about the Chinese room argument and robot play, and we kept on having the example of processing cats, interacting with cats. So, well, here's my little promotion. But you just mentioned that this work was sort of inspired by the dual coding theory by Allan Paivio, and this idea that we have visual and verbal distinct knowledge encoding systems. And I think that fits with this idea that, well, the brain is has functionally specialized areas, but we'll talk about the brain later because we have so many questions, right? So in some of these tasks, 3D simulation tasks, you're asking the agent to sort of bind objects to words, but in one of the tasks, you also ask the agent to bind words to category words or objects to category words. And this links back to our earlier discussion on analogy and the work you did in Cambridge. I was wondering whether there are maybe in the future ways to build specialized architectures where you focus on either processing categories based on features or categories based on relations. Sort of my intuition is that most of the current work focuses on categories based on features. And how would one train an agent to focus more on sort of relational categories? And is there any work you're doing on that?
Yeah, it's a great question. So, I think the analogy work was an example of really forcing the network to focus on relations rather than on features. So, I think that shows that it's possible. But in that case, we had to really force it by, a process which is a bit like meta training the network. So we gave it many, many examples of the necessity of focusing on relations, and eventually it acquired this ability. I think the more interesting question maybe is what sort of general experience might be necessary for a more generalist agent to have this ability to focus on relations, and how might that emerge? Yeah, I'm not entirely sure. So maybe there could be some mechanisms which support this. I think that self-attention, this mechanism in transformers, is really nice, right? It's a kind of nice soft compromise between a sort of symbol binding situation. One of the nice things about self-attention, it's a somewhat context-free memory, and the content-free, in the sense that they're all derived from the same core, but you have separate key, value, and query representations. And so this allows for a small amount of indirection or a small amount of separation between the information we use to find a variable and the content of that variable. And I think that's quite nice, but it's a very soft constraint, because I do feel that most cognition, apart from this variable binding thing, a lot of cognition is kind of content dependent, right? Context dependent. And self-attention is context dependent because all of these key, query, and value representations are derived from the same core representation at the layer below. So it's a kind of nice compromise between this kind of variable binding, indirection, or content-free operation and a context-dependent operation. So I guess that's an example of a bias which I think might be helpful in encouraging networks to focus a little bit more on relations and a little bit less on features. I would think very hard before building a specialized architecture for anything. I would instead first think about if there are ways for the whole learning system, including the data, to acquire the necessary behavior. But of course, it may be necessary to have a specialized architecture. So I'm not ruling out the necessity of that.
Yeah, besides architecture and the way that data is presented, I guess the more multimodal you make a model, the more relational it might think anyway, because then with the Roman example of the sounds and the waves, like that's vision and auditory. Once you have some sort of model with 7 different senses, then that might do it emergently.
Yeah, I would completely agree with that. I'm not saying that's definitely true, but I'm saying I completely agree with your intuition.
Okay. Well, I'm hopeful for the future. So my next heading is inspirations from neuroscience and psychology. And a lot of AI research, and especially at DeepMind, there's quite a rich history of taking inspiration from neuroscience. But then there's this debate of how much biological detail should be implemented in the model. And often on the AI side, well, people decide to take less detail than more detail, right? And you co-authored a paper with James McClelland where you made some comparisons between the brain and NLP. And for example, there were some comparisons between the medial temporal lobe and decree-based attention systems, which you sort of alluded to, and this idea of an external memory, which links back to the dual coding work. And making use of these examples or others, what is your take on how much biological details should we take from neuroscience?
Yeah, that's a great question. It's one I'm not that qualified to answer in terms of neuroscience, right? Because I'm not a neuroscientist, and I know that this question is being actively discussed amongst a large community of people interested in both neuroscience and machine learning. And that is a brilliant community. I think that such a community has already existed, but I don't think it's ever been as exciting or as rich as it is today. So I would encourage people to engage with that community who know more about this question than me. But in terms of cognitive science, I would say we should take a lot. And I suppose the controversial thing I'll say is, I think we should take a lot from cognitive science and more cognitive linguistics. And we should take a lot more than we should take from theoretical linguistics or linguistics that's not empirical in some way. But that's very controversial. So I'm saying that as a sort of spicy take that people can disagree with. I think cognitive science is important, partly because if you look at all the big contributors to modern AI, Hinton, Rommel Hart, to some extent, Jan LeCun and Joshua, almost all of them have some background in psychology, right? There's Paul Smolensky. There's like lists and lists of people who started or had some time, spent some time as a psychologist. So I think this notion that psychology is maybe some sort of soft discipline, which isn't analytic, I think you should, if that's your perspective on psychology, you should have a long conversation with Jeff Hinton, I would say. But those are incidentally the people who've also, I think, had the right intuitions when it comes to AI. And I think that combination is really telling. And I think part of it is because ultimately, what are we trying to do with AI? I think we're trying to create stuff that's useful and interesting for humans. And if we're trying to do that, I think it makes sense that if we understand human users better, we're going to understand how to build such a technology better.
So on the NeuroAI community side, my favorite podcast is Brain Inspired by Paul Middlebrooks, and I can really recommend that. That's great if you want to slowly move into NeuroAI and maybe you're only familiar with one of the two disciplines or neither of them. It really is quite a good way to get into it. On your kind of spicy point that maybe we should take less inspiration from theoretical linguistics, it'll be interesting to ask Alex Laskridis this afternoon about that, because that might get interesting. But let's go to the next question. So this is about inspiration from psychology, not neuroscience. And so you wrote in a paper with Andrew Lampinen, discuss how this concept of chunking might allow for mental time travel and how it can improve memory recall in a reinforcement learning language model. And can you tell us a bit more about that, please?
Yeah, so I think if we think about what I said earlier about the transformer, it's a brilliant memory system because it allows you to connect things in the past to things currently very easily. But it's not a perfect memory system because it's only 2,000 tokens long. And that might sound like a lot of words, but what if you're trying to model a video? That's not a lot of frames in a video. That doesn't get you a lot of context. And so it's very reasonable to think that there may be things which happened to 20,000 or 200,000 time steps previously that we might want to be able to consider now. If that's the case, transformer's not going to do it for us because we just can't go back far enough in time using the transformer's normal window of scope. And another important thing to say here is that I talked about events in the past. I didn't talk about things in the past. And this is because when we do retrieve from the past, I don't think we want just one thing, right? We're not picking up we're not like, give me an example of a cup. That's actually not a very useful memory. A useful memory is something that happened. And it's useful because there I can understand facts about the world, right? Like in language, that would be like a proposition, right? A sentence is a much more useful sort of unit of meaning than a word. And so really, if I'm going to want to create a system that answers questions, I'm going to need to be able to retrieve facts. I'm going to want to retrieve facts. And if I'm building an agent which needs to understand its world, an agent which knows what to do at a given moment, I'd like an agent which can think back to a particular time in the past when it was in a similar situation, think whether or not that went well or badly. And if it went well, to try and do something similar now. Both of these cases, I think you can see that having just the last 2,000 time steps in your memory is not necessarily going to be enough. So this motivates research into something that we might consider to be like an episodic memory, a memory of particular events which happened at any time in the past. And Andrew's work on mental time travel was designed to kind of take a transformer and make it a little bit more capable of episodic memory. His version was a somewhat hierarchical situation where there was one aspect of attention, Well, you can imagine the current transformer looks back at the last 2000 time steps. In Andrew's memory, there was one operation which first looked back at the last, say, 5 or 6 transformer windows. And then within each of those windows of 2000 steps, it looked for particular relevant events. And it was able to retrieve back from those, pull through these events. And so it allowed the agent to transfer back in time 4 or 5 times further than if it had just had a transformer memory. Now, there are many other technologies which are aiming to do something similar. So Andrew's version of this, the hierarchical transformer in an agent, was only one such example. And there's other things like the transformer XL, compressive transformer, and various other ones. So I would encourage people to look at those as well. Another development that's happened in text-based modeling, although not really in agents, is this idea of retrieval. This is kind of like an extreme episodic memory where almost anything that exists in a corpus is first embedded into some continuous space. And then a model is trained to kind of model text by predicting the next word, but also by looking back at these embeddings of all of the stuff that's happened in the past. And this is only possible if you have a large amount of memory, right? Like a big computer that can represent almost each individual paragraph from the past and store it there. And systems like this are starting to be effective. So that's another example of a type of episodic memory. It's not particularly biologically realistic because you kind of just remember everything. And so you do need an enormous memory. It won't scale potentially to an agent because, it's one thing remembering everything in a large text, but what if you have to have a video representation? You might need some sort of compression. And also you might have to investigate things like selective writing. There might be knowledge that you have which tells you whether or not you want to write something to memory or whether you don't. Because if you're able to filter in that way, you're going to save a lot of space. And ultimately, even with computers going the way we're going, it's still going to be beneficial to save space. And so I think there's a huge amount of research still to be done on memory, on what's the best way to retrieve memories, what's the best way to write memories, or should we write everything? And what's the best way in what format should we store our memories? What's the right way to compress our experience? Clearly, we don't, as humans, when we remember an event from the past, we don't remember literally every single detail. We only remember the important stuff. And so, kind of like it would be nice to move towards systems which were capable of doing something like that. And I don't think we have them at the moment. And I think it's a real exciting area of research.
Okay, so let's talk about some career questions. You're working at DeepMind. What's your favorite thing working there?
I think my favorite, honestly, the thing I love about DeepMind is it's full of scientists from different backgrounds. It's not a computer science company. So, they were very tolerant of the fact that I didn't have a computer science degree. Indeed, many of the greatest scientists or the best scientists there don't have a computer science degree. I don't know some basic stuff about computer science. I can't write code in C++. And nobody makes me feel small or unimportant as a consequence of that. I think we've got physicists, psychologists, social scientists, a bit of everything, computer scientists, they're all important. But there isn't this kind of, I hate to use the word macho because that sort of genders it, whereas I don't think it's really necessarily a gender thing, but you'll forgive the connection that I'm sort of loosely making. But with this sort of thing where there's something superior about computer science and potentially about the very analytic sciences like physics that's sort of superior to other areas of science, whereas I think they're all equally important in what we're doing in AGI. So that's what I like about DeepMind. And I'm not sure that's the case in all similar environments.
Yeah, I think talking about all of the big figures we mentioned today, I don't know, George Lakoff, James McClellan, Jeff Elman. I think with all of those, as you said, it's that interdisciplinary. So I think that's great that DeepMind encourages that. So a lot of listeners probably already convinced that they want to work at DeepMind. It's probably their dream place to work. And I guess it's quite competitive to get into. What advice would you give to young listeners who are thinking about maybe applying in 5 years when they have learned some things?
Yeah, well, firstly, I should just say that it doesn't just have to be young listeners, right? I think it could be a great place to work for older listeners too. Then I'd also say that I suspect this looks more daunting to people outside of DeepMind now than it did when I was not working at DeepMind, in the sense that, the company has grown a lot and interest in what DeepMind does has grown a lot in the time I've been there, about 6 years. So I can't necessarily relate as well as I should do to what things look like as an outsider now. But I can imagine that it looks very daunting. just because things like that always look daunting to me. And I remember what it looked like when I joined DeepMind. It did look very daunting. It'd just been acquired by Google. And I didn't think I had the necessary skills. But I guess I had gone and done some work with Yoshua Bengio in Montreal. And that gave me a knowledge of deep learning that I think wasn't common amongst European graduate students. And I think in the end, that was probably what sort of made it possible for me to join DeepMind at the time. Now, of course, things have totally changed. So I would say the most important thing is, if you're the sort of person who thinks you're probably good enough for anything like that, then you may well not be. If you're somebody who's worried and finds it all a bit daunting, that's probably entirely consistent with you being a great candidate who would easily fit in very well at DeepMind. That's not to say that I've given any actionable advice. I would say in terms of actions, I don't think you need to be interested in computers, but you probably do need to be able to program a bit in Python. If you want to do any sort of engineering or science roles, then you want to be able to program in Python, and you want to be able to get stuff done quickly. It helps if you're a graduate student. I think a good sign for me would be a graduate student, say, or a master's student who's done a lot of stuff. That would be stuff like, a real passion and interest in the area, clearly drawing connections between disparate areas of research. And obviously that can often reflect itself in things like people's GitHub repos. So they've done a lot of research themselves. They've shown this sort of initiative to go and discover new stuff. And then they put together a GitHub repo and tried some coding. And on the engineering side, getting some stuff working, writing blog posts and demos about what happened can be very valuable. And on the science side, obviously, the usual metric might correspond a bit more to papers. But on papers, I would say it's much more important to have said something really important and interesting in your papers than to have written a lot of papers. Optimizing for quantity, I don't think is really the thing. Obvious for research scientists, certainly, you have to be able to know where you're going, right? I think that's really the key skill of a research scientist, is to be able to look at the panorama of research that's out there, decide on a good path, decide on a good 1-year path, a good 3-year path, and take yourself there. Now, of course, you're going to be working with loads of other people, and it's going to be very collaborative, but I still think that internal self-guidance is a critical capacity for a research scientist. So I would definitely recommend sort of thinking about that. And then you don't have to build big models, right? These big models that you see coming out of the big tech companies, it's just not practical that people outside would be able to do that. And in fact, it's not even desirable, I think, that people doing it, say students and stuff, are doing that. I think what's more important is if maybe you can get access to those models and you can give a new take on how they're behaving, or maybe you can do a small scale simulation of something that's important to one of those models. So I think it's good to have plausible story about why your research might scale or why your research might be relevant to building a large scale system, but it's not important to have done that. And in fact, there's so much parallel complementary research that needs to be done in understanding or in really drilling down on what's going on with these big systems, that is a much more valuable thing to be doing than attempting to build one yourself. And then finally, I guess a lot comes down to personal relationships, right? So do contact people, meet people at conferences, try and be brave. People are kind in DeepMind. You might not be the most confident or outgoing person, but that's okay. But you do have to be able to sort of, I suppose, execute some of the normal functions of human beings, writing and asking for advice, writing and asking for help, and getting to know people in that way. And that can also, I think, make a huge difference.
Yeah, on the last point of contacting people, I can just say that from my own experience over the last half a year, I've emailed people where I thought, oh, they're so famous, they're so busy, they won't respond. And they respond maybe even on that evening and are really kind and really helpful. I think that's something maybe about the science, maybe the whole world is like this, but I think the science community, people really love what they do. So they're always very welcoming and responding to these questions.
Yeah, first thing I should say is hopefully a bit of an outlier, but when you emailed me about this podcast, I think I took about 3 weeks to respond. And on top of that, I needed a bit of a chase. And I think there's a good example there, which is, it happens that I had a particularly busy few months to do with personal stuff. I'm going to get married and stuff. And I just didn't have the bandwidth to cope with this. I've kind of learned my own lesson, which is you should always try and make the bandwidth for these things. But also there's an important thing, which is that you kind of chased it, right? And that's good. If you don't get a response, it can be just that people are busy. And there's no harm in a bit of a chaser, because often that will just go, you'll hit a convenient time and then you're going to get the response you want. I'm not trying to outsource the effort onto the part of the person contacting people, but it's just probably a reality of life that maybe a few chasing emails can make a big difference. And don't be afraid of chasing, what's the worst that can happen? I don't think everyone understands that chasing just shows that you care about what you're trying to do.
Yeah.
And Joshua, I sent Joshua Bengio an email when I was, in about 2013, probably in the middle of my PhD. And he responded within 3 minutes and then said, yeah, let's do a GVC. Now, of course, at that time, he wasn't quite as well known in the sense, right? Because a lot of what he's done at that time has then gone on to become incredibly famous. But it was telling that I sent emails to a bunch of people, and it's almost like the ones who responded quickest, it almost correlated with maybe the H index or something, or it correlated with how we might consider who the best scientist was. As in, there was a positive correlation between the speed at which they responded and those things. So I don't know what that says about being busy and things.
I think for sure you will be an outlier in terms of the quality of the research and how quickly they respond, because I know that with a few other people, where they were famous, they responded immediately, but I definitely say I'm a big fan of your work. So you definitely don't fit into that regression. Also, a really practical thing on the following up with people. A big thing I noticed with the podcast is that I land in people's spam folders all the time. And then you can just do is triangulate. If you contact the person in the university who maybe from some sort of connection, then they can send an email and then that works out. So that's a massive thing. Okay, one more career question. Someone getting into NLP right now, so maybe just starting off with their first online courses and maths and whatever. What is the most important thing they should learn?
Yeah, I would say you obviously want to learn about deep learning. So how neural networks work, a little bit of linear algebra, a little bit of multivariable calculus, like what a gradient is in multiple dimensions, those sorts of things. And then I would say psychology, in particular, experimental methods. So firstly, psychology as in some stuff about how humans work. I think that's important. I think more and more being good at NLP will be working out what to do with these big models, and working out what to do with these big models will require understanding humans. So I think that's important, more important than understanding Chomsky hierarchy, formal languages, or any of that stuff. The other thing I would say from psychology or any sort of natural science is the empirical methods. If we think of a massive model, like a massive language model, as something approaching the complexity of understanding an animal, then you're going to need to be as good at science in the true sense of the word as psychology graduates are, or as neuroscience graduates are, or as graduates in experimental physics are. And so you're going to need to know what a hypothesis test is, how to design a good experiment, how to control for a bunch of potential factors, all of that stuff. I don't want to suggest I'm a master of all of these myself, but within our group, I think we have all of these skills. And I think I'm very pleased that we do.
Yeah, that sounds really good. So my last header is sort of looking to the future. What science problem keep you up at night? What is sort of the toughest problem that people in NLP or maybe your group yet have to solve and are thinking about a lot, but it's just out of reach?
Yeah, I would say it's this thing about how these models relate to people and how they can continue. So how big models of language or language and vision or agents can be kind of taught to do useful things using people and people's ability to teach and people's ability to create data. So whether that's passive, they just kind of do it a priori, create the data and then train the model, or maybe it's an active process where in interaction with these models, humans are getting intuitions and learning to train them. There's also a load of stuff we're learning about how to actually distribute and clean data. Often in the papers, the tech reports which describe these big models, it's in the very end of the appendix. There's all sorts of tricks they use to rebalance the data. Hardly anyone talks about it because it's definitely not valued as a scientific contribution by the culture, which is a real shame. Because actually, I think there's an awful lot we need to learn about rebalancing and what types of data are important and all those things. But nobody, you don't get kudos from the big deep learning crowd for working out a new way to balance the data. So usually people just kind of don't even mention it.
Yeah, I feel like for good science and reproducibility, it'd be great if people know where to start with those things, because I assume everyone sort of tries to figure it out on their own. And then, well, A, it's harder, and B, is it as comparable if you don't know what you're comparing to, if it's just at the bottom of the appendix?
Yeah, exactly. Yeah, that's a problem it's a very immature world, right? These big models. So, there isn't even the right format because you can't fit all the details into a submission to NeurIPS or something like that. So there's not even people are writing these long reports, which is great because there's lots of details, but maybe not the right details. And there isn't a community or a culture of exactly how to report that science. So I think, it's very immature, but that's not a criticism. I think together it will improve, and the community will slowly improve on that.
Yeah. Can I say this was really good chat? I really enjoyed it. And also have to say, I really enjoyed reading your work, and especially the way you structured your website. It's quite a narrative feel and going through the topics, which made it a lot easier. And I can really recommend it to everyone to have a look at your work. And thanks a lot.
Yeah, thanks, Axeli. It was really fun chatting with you. And I think this is going to be a great podcast. Not necessarily the one I'm in, but the one you're creating.
Awesome. Thank you very much. I hope you enjoyed this episode. This has been part 1 of a double episode on linguistics and NLP. For part 2, I will talk to Alex Lascarides from Edinburgh, who will tell us a bit about her work on logic, discourse, and gestures. To find out when this episode is coming out, follow me on Twitter. Enjoy the rest of your day.